Okay, this is what I'm calling a spectroscopy combo example, where we're going to take a whole bunch of data to determine the structure of a molecule. So we're going to do a combustion analysis, and we're going to take a mass spectra, an infrared spectra, a proton NMR spectra, and a carbon-13 NMR spectra. And we're going to put all this data together to come up with the structure of our compound. Now, so that you can do this along with me, I've uploaded all of this data to files on D2L. So if you want to download that, you can take a look at that while we're working through this problem. All right, so here's sort of a summary of all the data that we have. And I'm going to kind of break it down into steps so that we'll be able to see everything a little bit more clearly. When I'm given one of these problems, generally the first thing I attack is the combustion analysis and see if I can come up with a formula for the compound. And I'm sorry, it looks like there's a typo here. There should only be one decimal place there in the carbon percentage. So what we're given from this combustion analysis is a percentage by mass of each one of our compounds. So what we want to do is get these into moles, because I can use that to determine the formula. And so the easiest way to do that is to assume we have 100 grams and then convert that into moles. So right, if I divide these by the molar masses of each of the elements, I have that many moles of carbon. All right, the next thing we do is divide each one of these numbers by the smallest one so we can get the relative moles of each atom. So if I divide them all by 1.95, then I get 2.5 for the carbon, 5 for the hydrogen, and 1 for the oxygen. Now, of course, I can't have half a mole of carbon, or I can't have half of a carbon atom. I guess I could have half a mole. So I want to multiply all of these by 2. And so my empirical formula is going to be C5H10O2. All right, let's go to the mass spectra next. All right, so at the top, I'll summarize what we know so far. So we know the empirical formula. And so let's see, based on our parent ion peak, right, this should be the molar mass of the compound. Let's see if this matches what we get when we add up the masses from the empirical formula to tell us if we need to scale this by an integer to get the actual molecular formula. So 5, oops. And so when I add all of those up, I get basically 102. Right, so not only is this the empirical formula, but now we also know that it's also the molecular formula. All right, the next thing I generally like to do is determine the hydrogen deficiency index, right? That'll tell me how many double bonds and rings I have, right? So I take the carbons, multiply it by 2, and then add 2. So 2 times 5 is 10, plus 2 is 12. So to be saturated, I'd have to have 12 hydrogens. I'm 2 short, so that gives me an HDI of 1. So I know that I have 1 double bond or ring in my compound. We can also take a look at our mass spectrum and see if we have any obvious fragments. And so if I do 102 minus 87, right, that means I've lost 15. So I've lost probably a methyl group. 87 minus 71 is 31. That's not one of the numbers I have memorized, so I'm not sure exactly what that is. 102 minus 59 gives me 43, right? I know that one. That matches up with a propyl group, so I've probably got a methyl group. I've probably got a propyl group, and then this 43, right, that's the propyl group that I've probably lost in that fragment. So I've probably got a methyl and a propyl in my compound. All right, I think the next place that's good to go is the IR spectra. And they've helpfully drawn in the lines for us already at 1500 and 3000 wave numbers. Right, so remember, we're going to ignore all of this junk down here in the fingerprint spectrum. We're going to focus on the diagnostic region. So I've got my CHs. Maybe more interestingly, right, I've got this big peak at just above 1700 wave numbers. Right, that is the signature of a carbonyl. So I almost certainly have a carbon-oxygen double bond, right? And then it also takes care of my HDI, right? That's where my 1 degree of unsaturation probably comes in. And I don't see much else here. There's this little double peak up here, but I don't have any nitrogens, so it's not like that's a primary amine or anything. And I've already used up my HDI, so it's not like that's a carbon-hydrogen stretch from a carbon-carbon double bond or triple bond or anything like that. So I think that's probably just noise. And so I think the main information we can get out of the IR spectrum is that we have a C double bond O. I guess the other big thing that we can tell from the IR spectrum is what it's not showing us, right? So we've accounted for one of the oxygens, but there's still another oxygen unaccounted for. And I think the likely things it could be is an alcohol, because I don't have a big, broad OH peak in the IR spectrum. I almost certainly don't have an alcohol. So what that tells me is, in connection with this carbon-oxygen double bond, I maybe either have an ester, or in addition to the carbon-oxygen double bond, somewhere else in the molecule, I have an ether. Although with a molecule that's not very large, having a carbon that's not an OH with a carbonyl means I'm thinking I probably have an ester. All right, so again, I've summarized kind of everything we know. We now are going to go look at the proton NMR spectra. And so I have 3 signals. So I have 3 different types of hydrogens in my molecule. And that would sort of account for, right, if I have a methyl and a propyl, right, here's 2 types of hydrogens. Here's 1 type of hydrogen. And then, right, very characteristic of an isopropyl group is what I have right here, right? When I have a septet, 1, 2, 3, 4, 5, 6, 7, with an integration of 1, and then I have a doublet with an integration of 6, right? This is the signature that I'm looking for to tell me that I have an isopropyl group. And then, right, this here singlet with integration of 3 tells me that I have an isolated methyl group. So I've got a methyl group that's not adjacent to anything that has hydrogens. So I think we can take all the information that we have and go to sort of some scratch paper and see how I could possibly put this molecule together. All right, so based on the previous slides, this is all the information that I know that I have. And I think we've actually accounted for all of the atoms in the formula, right? I have 1, 2, 3, 4, 5 carbons. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. I've got my 2 oxygens. So these are all the pieces. We just need to see how to put all of this together. And if you want, you may want to pause this video and see what you can come up with. See what are all the different possible formulas you can come up with. Okay, if you're back, I'm guessing you've got some possibilities. I was able to come up with 2 likely possibilities for potential formulas. Well, yeah, we'll do CH. So I think we possibly have this ester, or this ester. This is really the only 2 ways that I can see putting everything together where, everything is obeying the octet rule. So let's go back to our proton NMR and see if we can distinguish between these 2 possible esters. All right, so we've redrawn them here a little bit neater than my drawings on the last page. And so what I want to see is how far downfield are the methyl group and then the CH2 group on, the CH group from the isopropyl. So we can see that the methyl group is shifted way downfield, right? And so I think that's more consistent with this picture, right? When I have something next to the oxygen in the ester, right, that tends to get shifted 3 ppm downfield. So a CH3 would normally be about 1, maybe a little bit less than 1, right? And then the fact that I'm shifted the methyl is all the way down close to 4, right? I think that's a pretty good indication that this is the structure. When I'm next to a when I'm next to a carbonyl like this CH is, right, that's generally going to shift it downfield 1 ppm. So a CH is normally in this region, and so being shifted about 1 ppm downfield, right, I think again is consistent with this structure. If we had this molecule, right, then I think the septet would have been further downfield and the methyl group would have been less downfield. So based on the chemical shifts, I think we can identify this as our likely candidate. All right, now we haven't looked at our carbon-13 data yet. I think we know what the compound is, but it's good to see if this is consistent with what we've come up with. So we've got a singlet with a very large chemical shift, right? And so I think that's consistent with this carbon, right? It doesn't have any hydrogen, so it's a singlet. It's attached to 2 very electronegative oxygen atoms, and so we'd expect it to have a large chemical shift. The quartet would be consistent with a methyl group, right? And so I think this methyl that's directly attached to an oxygen, right, is going to be fairly shifted fairly far downfield. So I think this second peak, or the second entry, is consistent with this methyl. I've got a doublet, so that would be consistent with a CH group, right? And then it's attached to the carbonyl, so it's shifted somewhat downfield, but not as much as the ones that are directly connected to oxygens. And then I have a quartet, right? Both of these CH3s are identical, so they're only going to give one signal. They're both going to contribute to a quartet, right? And then it's furthest away from all of the oxygens, and so it has the smallest chemical shift. So I think our carbon-13 data is consistent with the structure that we've come up with. So when you're doing these problems on your own, it's not in exact order of things, right? The way you approach it may be slightly different. You may need to go back to the mass spec after you have potential structures to tell them apart, but you get an idea of what my thought process is on doing these problems.